Hello, everyone,
Hello from Alessandro,
and Abe.
and welcome to another episode of In Conversations.
Yeah,
So until now we have talked a lot about OpenRender and some bases and many things that you can many episodes that you can find. I don't know how many, like 8 or 9. I don't remember.
there were 8 or 9 sessions.
Sessions,
but
right? The episodes is much more,
Yeah.
much more. But in this case, we thought of telling you something a bit different. So, how essentially trying to illustrate how OpenRender makes our ideas and making art in a certain sense easier. Starting from a simple concept and then allowing to follow the flow of your thoughts when you get comfortable with the API and be surprised as we were at what you get at the end. So what did we start
But one
with
thing,
this
we're
time?
going to do it a tiny bit different today because we're not going to be live coding. We're going to look at, I think, 9 or 10 programs we wrote during the last hour. And we started with this, like the simple idea of a bouncing ball in a box. This is, I think, probably it might have been the first program I ever wrote in my life.
So this is a classic. This is something that it's almost 101, 102 in creative coding.
Yeah.
So essentially you have a particle and you have a box and you simply have make it bounce. People would say in an elastic way, but we don't care about this terminology. The fact that you see at screen that the velocity is reflected on the boundary, that's what it means. And there's a very simple way of coding this that we can show, maybe.
So the simpler way,
we're
not showing.
Okay, the simpler way we're not showing.
Because you can write it without creating a class like we did here,
okay, yeah,
a mover.
right.
You
That's
can
right.
also write it by having the bounding box would be the whole window. In this case, we create a boundary, so
Correct.
you can see it a bit
Yes.
inside.
Exactly.
So we create a boundary, which is basically the window offset inwards for
That you see in pink now, right?
100 pixels. And then we created this mover object, which starts at the center of the screen.
But why? Okay, so I think that's a question, since we're talking about how we prototype, why we decided to create a mover object.
Right.
Yeah.
So we wanted to go further and not just work with a rectangle.
Yeah, and so this was an easy way for us to reuse code and to prototype with it once we had this in place.
Yeah.
Okay, so can we look a bit what this mover object does?
Yeah. So when we construct it, we pass it the initial point and a velocity. We have the class up here. It has 3 methods.
Yeah.
An update, an internal function that checks if it hits a boundary or the border, and then it can mirror the velocity. And finally just a draw, which is very simple.
Which we can say is a bit like the basic ingredient of a mover recipe, right? All the time you need an update. You need to know, where the mover is going to be next. You need a way to draw it.
Yeah.
And if you have a boundary, you need a way to check if it's on the if it's touched the boundary or not. And that's what we have done here.
In this first version, when we update, we pass a rectangle. So this is not yet like a generic thing, because what we wanted to do is to be able to pass any random shapes, like triangles or circles or any weird stuff.
And if you look at the code, it's the classic for if condition that when you bounce on a square, right? One for each of the sides, right? And so at this moment, the rectangle is nothing that a collection of this information of where the corners are. There is no more, no less. So this is really like 101 boundary, I'd say collision or reflection that you find almost everywhere.
There's one interesting thing, because things are immutable here.
Right.
You cannot say here like pos x equals b max x but you have to create a copy.
Yeah.
And then modifying either the X or the Y when making the copy.
This is one of those things that you get to learn when you use OpenRender. I mean, the position and velocity. I mean, the vectors are, and all operation on vectors are immutables on the vectors class. But okay, so we started from this thing, this case, and then we thought like, how about can we make bouncing balls where the boundary is irregular? Okay, so now one strategy that I personally would have followed, say 10 years ago, was to start already with a complicated shape, right? Without having done the step that we just showed you. Like, okay, so if I have a rectangle, is in the way we have described before, we still use all these things like the X coordinate, the Y coordinate, things like this. Can we make it more general than, it doesn't use this, and that's the first idea. And in OpenRender, this translates to a class, right? To a certain abstraction.
Yeah, and in this, I'm showing now the version 2 of this program. We still didn't go past the rectangle.
Exactly.
But the difference is that we are passing a shape contour. This is no longer a rectangle, it's not a fixed shape, so this could be anything. It could be a circle, a triangle, any shape. And then we have to use a different approach because we are not looking the horizontal and vertical bounds of this rectangle. But what we do is, in this experiment, we do these two checks. First is, are we still in the boundary? And
notice that now somehow we are assuming that the boundary are closed without telling anyone, also ourselves before, but you'll see how this evolves. But so now we check that it's in the boundary, and if it's so, what happens?
Well, if it's not in the boundary, that means that we are outside. So we want to bring the particle back. So we revert the velocity just by a random number we tried here to seem to work.
To bring ourselves to the condition in which we are sure that the particle is inside the boundary.
This is a bit like an undo. You give us a step if you are outside, then go back. And then what we do is look for the nearest point in the boundary. And
that's the first real use now, or this is where OpenRender helps you, because this abstraction like shape contour, they have a function already that tells you this is the nearest point.
So this doesn't give actually a point, but an object of contour point, which has some information. One of the properties it has is actually the position, which is what we care about. So then what do? We calculate the difference between where we are and the nearest point in the boundary.
So we use some classic 2D geometry, like in saying, what does it mean that a particle reflects, a plane surface? It means that there is a normal to the surface and the velocity is reflected according to that normal. So we construct the normal.
And then we can call this reflect using that normal.
Exactly.
You can see that then the cool thing about this is we no longer have 4 cases for X, Y, but it basically doesn't care. It just searches for the edge which is near, and then it reflects using that.
Exactly.
What is the second case here?
The second case is, the second case is that is to... Even if the particle is in the boundary, right? It might be close enough to the boundary that at the next step it might be outside of the boundary. So this is kind of do-it-yourself solution to avoid that. So instead of saying the distance between the point and the boundary needs to be 0 for you to reflect, no, do it like with a small, buffer of space, so to avoid going out of the boundary.
You can see that these 2 lines are duplicated. So it's not mega optimized. The reason is because in this case we changed post before, so we cannot lift this outside.
Exactly.
So then we calculate here the distance, how far are we, and if we are too near to the border, then we do again the same thing. This is the same line and the same line here.
So until now, then you see that nothing has changed, right? But we did something that seems trivial, but is very useful. We rewrote this in a way that whatever now the boundary is, this code still makes sense.
Yeah.
It doesn't need to be a rectangle. It doesn't need to, because we are not talking about coordinates anymore, but we are talking about properties of the object, like the ability to tell you a nearest point. So now, every time you have the nearest point kind of method, you can use this technique.
Let's look at the third example.
That's what we...
What did we do here? What kind of boundary? Here we're creating a hobby curve.
Yes. So now now this is the first step into wiggling the boundary, let's say like this.
Yeah.
And you can see now that the boundary is irregular, but the particle is still reflecting.
The program is, I think, is still the same, right?
It's still the same.
We haven't changed.
Because until this moment, we still were convinced that boundaries need to be closed. And so the first check.
Yeah. The only difference is this. Before we created, let me show it again, a rectangle.
Yeah. There is no other difference between these two programs.
Here's the boundary. We offset the borders.
Yeah.
We create a contour in the version 3.
See you tomorrow.
See you. In the version 3, we basically create a different shape. That's it. How you create it? Well, it's a wobbly curve with 16 points.
Yeah.
And they are centered around the center of the screen. We use polar coordinates, and basically the angle increases uniformly, but the radius is random between 300 and 350.
And at this point, you can have any curve. You can have like a polygon, a closed polygon, and it will do the same. Like the code will work.
Yeah.
And this is already a step that I find it very interesting because, spending time with the API to use its, its internal mechanism allowed us now to open a space of possibility in which we don't have a simple square, but now we have a much more organic figure.
Where did we go next?
Where did we go next?
So let's see. Here we are still using a boundary hobby curve.
I think next we thought we had this idea.
Yeah.
Whoa, what if we have holes in our boundaries? So what if
well, we didn't get there.
We didn't get there.
Because we messed up.
We didn't get there, right?
But yeah, so what we did is create two boundaries.
Exactly. So we created two boundaries, and as you can see now, the particle, simply reflects on the inside or on the outside part with the same code, right? Yeah. We changed it a bit.
Yeah.
Because
what we changed basically is to create a shape instead of a shape contour. So now we draw here a shape, we pass a shape, and now here I said boundaries. So what we do is check all of the contours which are part of this shape.
Now we can see though that the code has a bit changed from the one before. You can see that the condition on being contained, now it's not there anymore.
Yeah.
Why? Because the particle is always not contained in the boundary inside.
It was getting confusing.
Yeah.
Because, for example, a point in the center of the shape would be contained by two shapes.
Exactly.
And we also wanted to make non-closed contours.
Exactly.
So the particle could escape.
Yeah.
But then you cannot get the in property of
because it's not defined.
Yeah.
For,
you don't know if. How do you know if?
So what we did actually here, and here it's where you can branch life divides into point. Either you find a way to hack it, let's say like this, and that's what we did with this distance less than radius dot 2.
Yeah.
So essentially we made it in a way that it's is visually appealing but computationally easy to implement. Or if you choose the other path, there is another way to make this properly.
Right.
And it's
the right way is more complicated because if you think a particle can have a high velocity maybe one frame is inside, the second frame is outside. When did it cross? So then you would have to calculate many steps between the in state and the out state, know when it collided, and then reflect and know the remaining step.
So this means that the integration algorithms, that's how they call this thing when you make this simulation, becomes more complicated. And from the visual and if you want the artistical point of view, it didn't matter, at least to me. So we decided to go another direction and ask another set of questions. And the next set of question was...
Here's where we
put many particles.
Lots of particles. Oh,
not
so many.
Not so many. But that's, for instance, another thing that I always like to do. I always like to create something for a single agent and then say, what happens when I have many agents? Because in general, things happen. Okay? So we have added all these particles. They are unaware of each other. At this moment. They don't talk with each other. They only talk with the boundary. Okay? And already it's fascinating to watch. I don't know. I like it. But
one aspect I liked is that they can go inside this shape clockwise or counterclockwise, and it's kind of random. Or how many you could count how many particles are right now going clockwise.
Exactly. And for instance, another idea that would be interesting, now I'm like thinking about it, suppose you have a line that cuts the figure, an imaginary line that cuts the figure in the middle, you can check for each particle how many times this line is crossed on the top. And you would know how many times it changes direction and use this information to drive, you know, some aspect of lights, color and things like this. So
so this program didn't involve many changes. It's just we converted
essentially no change.
One particle into a list of particles, and then basically you have to iterate to update them all and draw them all, and that's it.
And that's it. So, but now we have more particles. What did we think? Because we didn't stop here. We thought like,
let's see, version 6.
Let's see, version 6.
That's where we opened the contours.
Then we thought like, how about we put holes in the contour and check how many times, you know, particle escape. And then we said, why don't we put more than one contour? And so we created this little labyrinth. And we somehow spent some time observing particle escaping. Okay?
And sometimes, I don't know, we will see we have like a glitch. Which we have these particles that get attached to the walls.
To the wall. And now it's trapped there essentially forever, because also in this case, the particles are unaware from each other. So we were fascinated watching this for a while, but I think in our head, we still were not happy with how straight liney this is. I mean, it's fun to watch, but you can see that this motion are very, you know, escaped.
One escaped.
Very good.
2.
Good for you.
3.
2, 3. Good for you. So we were not very happy, or at least personally, I always observe these things, right? Like, what happens? I mean, this motion is very regular. I'll think about later, but I know that I will think about later. But now the new part of this code is like, we open. And how did we open?
So first we pass this false parameter to the closed property of the hobby curve. That's not enough because that would be visually identical. But then what we do is do sub. So you grab a part of this contour. So by not grabbing from 0 to 1, but actually from 0.05 to 1, then we are basically deleting a little part of.
That's another aspect in which is very easy. I mean, OpenRender helps you in the sense that you have this possibility to create pieces of curves from entire curves very easily. Then like what is it that we thought?
Let's see, because we didn't write a single comment.
Yes, exactly. Let's see what. I know what we did. We decided, you know what, it would be nice if particles interact. So
that's
we added an interaction method. So how do these particles interact now?
How did we call that? First we evaluate all the interactions, and then we do what we did before, update and draw.
And the interaction in this case is essentially a repulsive interaction. A particle is repulsed by another one as soon as this particle enters a given space.
Yeah.
Okay.
So you saw that the loop here at the bottom.
Yeah.
We go through all of them. Also, we have pairs of A, B, and I think there's even a method to get them by pairs. Anyway, we have A, B. We make sure that they're not the same, and then we check for the interactions. So we now have this pair. Check interactions, other. Right, so we calculate the distance between the two, and if it's below a certain distance with a magic number here, 5, that's basically, are they close to each other, then we update this force.
Yeah, and this 5 has nothing, I mean, just to be clear, it's nothing, how to say, you cannot deduce this number.
No.
You just have to do trial and error and see the outcome that you like the most. And we settled on this because we wanted a little bit of interaction, but not too much.
Yeah. If this number is higher, then they can notice each other from very far away.
Yeah, exactly.
And then this is how much force is applied.
And then maybe another trick and comment is that it's good in this case to maximize the velocity because otherwise your velocity is going to explode. So you want to make,
where did we do that?
A maximum amount of velocity.
So later in update, we apply the force, we just calculated, and then we reset it to 0. But then here, we normalize. And
these are those things that at the beginning that I didn't know. I was like, why are my particles all crazy? And I see other people think and they look nice and smooth. Yeah, because, there are this type of implementation, this type of things.
I think this exists also in nature of code. You can see.
Yeah, absolutely. Limit.
Yeah.
This is the way of doing that.
We didn't show this program in action.
Yeah, let's see what it does.
So
you can see that now they are interacting.
Yeah.
A bit, and here you can do interesting thing. For instance, the coefficient interaction could change per particle. There are many ways of changing this. But to me, also this, I mean, and this is a personal suggestion. Like, for instance, let's think about the coefficient of interaction for the forces, right? So if you select it randomly with a uniform distribution, you will see it in the final thing because it will be present as noise in the sense that it's not coherent, right? But if you use other type of distribution like Gaussian, normal, or even how to say simplex or things like this, it's correlate. You correlate it. But anyway, you can see now what this thing is doing.
One nice side effect of using the forces is now the particles that are trapped in those lines sometimes are liberated.
Yes, exactly.
So sometimes, I don't know how it happens, but some others get close and then they jump out of the curve. That's pretty cool.
And this already now gives you a system there is not, it's more than, let's say like this, is more than the union of its parts, because the various particles are aware of each other, they interact with the boundary, and so now they all sort of cooperate of, each one can escape or not, but it also depends on the other particles around.
One thing that came to my mind when seeing this was some kind of gas simulation.
Yeah.
As if you release some gas in the center and how it slowly travels to the outer world.
Yeah, exactly. And then I think at this point it was for us time to visualize this or not?
Yeah, I think so.
Because at certain point we were like, okay, this is a cool simulation.
Yeah.
But how do you make a piece and I think in my head there was a static piece, like an image, not necessarily anything interactive. How do you make anything that it might be interesting to see?
Yeah.
And then what we did, we accumulated traces.
Yeah. So to do that, we create a render target where we can draw the trails. And most of the program is the same, except that, let me see, somewhere we draw into, at the end. So we draw the whole simulation.
Yeah.
And one thing, I'm drawing the trails first. So that's the old trails. Then we draw a simulation. And later here we update the trails. So basically it's drawing again. So here you have mover draw, here you have mover draw.
And here the interesting thing is that we did this thing that, I mean, it's cool to do, to keep track of what's happening to the bug and things like this. Yeah. And then I think here the one of the idea was that the color was sort of related to the velocity. So the slower the particles are, the more intense is the color. I think that was the idea, I think, right?
Yeah.
Cool.
It's pretty nice to see the history of.
Yeah.
And you see the trapped particles again on the edges.
And these for us started looking at something that can be, as a piece of a simulation that can be iterated, then stop, and becomes a piece of visual art, a static piece that you can print, exhibit, or whatever.
Yeah.
Not that I don't like the animation, but it's nice to... the accumulated part looks very nice. One thing we were not happy with this is that at a certain point we realized that since the particles spend a lot of time in some region, the color might be very homogeneous.
Yeah.
And there might be,
It may end up all being very flat.
Very flat, exactly. There is no much detail. For instance, in this case, in the central part, you can see.
We fix this in the next one.
Yeah.
But before that, I wanted to just quickly mention what we did with the radios here.
Right, yeah.
Because I wanted to have different radios for the preview of those yellow dots and the little particles. So when we draw, we potentially pass a radius. If that radius was passed and is used, otherwise the radius defined in the agent is
this
used.
I think is a nice trick to extend function, allowing back compatibility in a certain sense. So we didn't have to rewrite.
So here we don't have to pass a radius, but if you do, then that one is used.
Yeah, and using the mouse position is a cool way to toggle in and out. Your data generating process, because the simulation, that's what
one of the most minimal interfaces
that you can do. But then, and we arrived, I think, at mostly the final form.
Yeah.
So what we did here, it's like, we did changes in different, different aspects. So we changed essentially, we started with this idea like, we don't like it to be very dense at certain point, right? So what we thought is like, okay, so to avoid that the colors are flat, why don't we change colors? And then we decided to change the colors, right?
Yeah.
In kind of time-based fashion, right?
Yeah.
Maybe we can show how we did it.
So we're now, when we're drawing, we are passing also a color. If we don't pass again a color, then it has a default, which is here. The default is yellow. So when I don't know why it's now pink, but if we pass a color, then it's altered internally, mixing between two colors. Basically,
exactly.
The color provided or this Indian red. And for that, it uses a sine wave, and it uses the age of the particle.
Yeah.
The age starts being 0, and every time we draw, it increased.
Yeah.
And then there's a tempo. So then each particle has a unique tempo between points.
Okay, so this is the original one.
Yeah.
Like that's how we originally taught it. So the steps for each particle increases, and the particle is unaware of anybody else, right? Now, when you have a particle system, it's always very cool to tie the property of an agent system with what happens to others. So we decided that that the step is also dependent on how many other particles, the given agent is, reacting with.
Right. So if the particle collides or gets near others, then it's increasing faster.
Exactly. So it means that now the way in which the color change is related to all the system, not just to the single particle.
And then one thing you wanted to add was we switched to blend mode add.
Yeah.
But this has the side effect that was making everything eventually white.
Yeah.
So then we thought, we could have some particles be additive and other particles be subtractive.
Yeah.
So each one has a unique random blend mode. And this is used here when we draw the particle.
Correct, yeah.
Yeah.
And actually this is interesting because in this final code, the simulation is the same, but what you play with is the visual aspect of it. There's nothing to do with, modeling anything, but it's just to find something that, you find appealing. And one technique is to change the way, lights or colors in this case are blended together. And this is the aspect that for me makes it different from just a simulation of, something that looks like a gas trapped somewhere. Even if that is the starting place. And then you get, something like you see on the screen. You can, and in my head there are tons of things that I would add, like should I add Perlin noise vector field below, and all these type of things. But I think what we wanted to show is that we started from a conversation on something very simple, something like, I've done this tons of time making particle bounds on the screen. What if I challenge their assumption that the boundary is a square and I move towards other, things? And hopefully it's useful for you, how, I don't know, this playful way of doing things, I don't know how to call it.
But what I noticed also then by being two of us here, we all the time get an idea of based on what the other suggested.
Yeah, exactly. But I think, I like this thinking about concepts, and then it's very easy as we saw. The code is a minimal change one from another, and with minimal effort. Like when we changed from one particle to 20, it was a line of code in change. And I think this is what I really like of this framework that allows to scale stuff very nicely. And hopefully this was useful.
Cool.
It's a new format that I'm liking a lot. And
let's try again another time.
Let's try again another time. Okay, so hopefully see you in the next episode.
Take care.
Bye bye.
Bye bye.